Hi, welcome to the last talk for the conference. Thanks for sticking around. My name is Omer Peleg, and the work I'll be presenting today is in collaboration with Adam Morrison and Dan Tsafrir from the Technion, as well as Ben Serebrin from Google. In today's talk, we'll set off with describing what an IOMMU is, how does it work, and why would you even want to use an IOMMU. We'll present some of the main challenges IOMMU support present to OSes, as well as why the current solutions offered by these OSes do not scale. And we'll offer some of our own scalable solutions and try and compare and contrast them. So what is an IOMMU? Well, an IOMMU is not unlike an MMU, except an IOMMU works on devices, on the DMA or direct memory access path. And when a device wants to carry out a direct memory access, it tries to access an I/O virtual address, and this request is intercepted by the IOMMU, which translates it to a physical address that can be accessed in the system memory. So how does it look? Well, when a device tries to carry out a direct memory access operation, it tries to access a certain virtual I/O virtual address, and the IOMMU intercepts that. It can look up in its own table of I/O devices and find the entry that corresponds to this device, which points to a page table. It can then traverse the page table and find the physical address that corresponds with the I/O virtual address the device has tried to access, and with that it can reformulate the DMA request and carry it out to the memory. So why even use an IOMMU? Well, for many of the same reasons you would use an MMU, and chiefly for protection. You don't want your devices to be able to access memory that do not belong. Once you have this mediation in the middle, and a device tries to access an address that it's not supposed to, it will simply be blocked. And that could be good if you have buggy devices or malicious devices, but your devices don't have to be malicious to begin with, right? You could be in the case where your device was perfectly fine, but at some point its firmware got infected, and we have seen cases of firmware malware out in the wild as late as last February. So using an IOMMU is chiefly for reducing your attack surface. So MMUs and IOMMUs are very much alike. Where do they differ? And that's mainly in the usage pattern, where in a process you would usually have a lot of mallocs and frees, but these mallocs and frees would rarely actually translate to needing a new page from the system or releasing a page back to the system, and only when it does, you would call munmap or mmap or nunmap, and only these mmap and nunmap operations would be translated to changes in the paging structure itself. With an IOMMU, the way Linux works, you have to carry out a DMA map operation before every DMA transaction takes place, and you have to tear it down using a DMA unmap after it concludes. So you have to have a DMA map and DMA unmap on any DMA transaction you have. And that naturally causes a lot more access to the page tables, and for the purpose of this talk, we're not going to change the translation layer in Linux at all, or any of the drivers in Linux. We are only going to touch the IOMMU driver itself and the way it operates on the page table. So how does the IOMMU actually affect performance? To determine that, we need to have some kind of a parallel workload if you want to estimate the scalability issues with an IOMMU. And for that, we'd use the aggregate throughput of 270 instances of netperf TCP request response running in parallel, each of them sending out a byte, getting a byte in return, and only then sending another one. And we can see that without an IOMMU, this workload scales quite well linearly in Linux. We don't see any performance issue with its scalability. Turning IOMMU on in Linux, though, causes a significant performance meltdown. You can get almost no extra benefits from the fact that you are adding additional cores. And the question is whether we attribute this overhead to the hardware overhead of translating each access to the memory, or to the software overhead. As we said, we have to do a map operation before every DMA transaction and an unmap afterwards. In an attempt to measure the hardware overhead, we have in the IOMMU system, we have run a special test where we've set all the mappings for all of our transactions well in advance. That's not how you're supposed to do that. We just want to do try and measure how long does it take the hardware to translate. And for this test and this test alone, we do not have any DMA map or DMA unmap operations going on in the system while we're carrying out DMA. And we can see that if we just introduce the hardware overhead of the IOMMU, we get virtually no adverse throughput degradation. So with that, we deduce that the overhead that exists in the system and exists in Linux is a management overhead, is the fact that we have to create and tear down all of these IOMMU mappings. And all of our solutions, scalable solutions we'll show later in this talk, will all perform very much like the no IOMMU throughput, and they will scale linearly. There is actually been a prior work in this field in a paper called EOVAR presented right here in this very hotel not 4 months ago in FAST of 2015. And EOVAR also tackles the IOMMU management problem, so we will use it as our baseline for the rest of the duration of the talk. And what EOVAR sets out to do is to optimize the single core performance of IOMMU management. And the question is, how does it perform when you try to run it using our parallel workload? Well, it performs way better than stock Linux IOMMU, but it still suffers from a very similar meltdown when it comes under parallel load. So in our work, we have surveyed a few open source operating systems. And while all these operating systems have their own notion of how to manage the IOMMU mapping problem, all of them have two very similar bottlenecks. Namely, all of them have to allocate an IOVA, or a virtual address, just the number of the virtual page in which they can set up the mapping. And all of them have to carry out invalidations after they do an unmapping, and we'll talk about invalidations in just 1 minute. And after we've explained why these bottlenecks exist, we'll try and present one solution for the invalidation problem and 3 designs for IOVA assignment, and we'll try and compare them with one another. So if we look on the cycle breakdown of our parallel workload in Linux with 16 cores, we can easily see the 2 bottlenecks we just talked about. And locks actually dominate most of our cycles in the system, and we'll start with the invalidation. The invalidation lock that takes most of our cycles. So why do we actually need invalidation? Well, IOMMU, very similarly to an MMU, caches translations it does. Right? It goes through the page tables, it finds what a virtual address maps to, and it saves it in the cache to be used again later. And after you have removed the mapping from the page table, you need to make sure that this entry in the IOTLB is invalidated. Both for correctness purposes, if you ever set this same IO virtual address to point to a new page, you can't have a stale page still in the cache, or in the IOTLB. And for security purposes, once you've removed an entry from the table, you don't want the device to be able to keep on accessing this page. So a naive way to do these invalidations is once you have removed something from the page table, just go to the invalidation interface and invalidate it. That is what we call strict invalidation, and the problem is that it's not really feasible. It adds a lot of contention because for each unmapping you have to go to the hardware invalidation interface and take a lock while accessing it, introducing a lot of contention. How bad is it? Well, if you remember, stock Linux IOMMU does not perform very well to begin with, and if we configure Linux to use strict invalidations, we get even way worse performance. On 16 cores, as much as 7% of the stock Linux IOMMU. So what does Linux actually do? Well, Linux batches up to 250 of these invalidations and then carry out one global IoT invalidation that invalidates all of them. And after this invalidation has taken place, it can go and free the IOVAs back for reallocation. Well, that introduces some vulnerability window in which the device can keep on accessing entries that were already removed from the table. It does not introduce a correctness problem because these IOVAs won't be reallocated until an invalidation has taken place. Okay, so what is the problem here? Well, Linux has to save all of these I/O virtual addresses to be freed only after invalidation has taken place, and it does that bookkeeping under a global lock. So when a CPU wants to carry out an unmap, it removes the mapping from the page table, and then it takes a global lock and queues its IOVA on a list. And another core would then take this lock and queues its own IOVA on the list. Another core would take a lock, queue its IOVA on the list. And once we want to carry out an invalidation, one of the cores will have to take the lock, carry out the global invalidation, and then free all of these IOVAs for reallocation. So, so here we note that it's actually not, the reason we are keeping the IOVAs on the side is for the correctness property. And the only thing we really need to satisfy here is that IOVAs are not freed for reallocation until we have made sure that no IOTLB entry exists in the system from them. And if so, we can redesign our invalidation, deferred invalidation mechanism to work with pair core data structures. Each core can just batch its own invalidations, 250 invalidations, carry out its own global IOTLB invalidation, and then go and free its own address. And that way, correctness is maintained because addresses are not freed until the core that is freeing then has carried out an invalidation. With that, hopefully, we have solved the invalidation bottleneck, and we'll go to try and solve the IOVA allocation bottleneck. So Linux assigns IOVAs from a globally locked allocator. And the way it allocates IOVAs is by traversing the virtual address space from the top until it finds a region large enough to satisfy the mapping. And in worst case, it could take linear time. Our baseline IOVA actually guarantees that it happens in constant time for our workload. And the nice property of this kind of allocator is that it bounds our allocations in a relatively narrow area and reuses virtual pages over and over again. And the reason that this is a good property for us to have is the way Linux manages its page tables. Basically, you don't want to have a lock on your page tables. It's an architected data structure. You only have one per device. And Linux is actually able to manage its page tables without taking any locks. And we go into full detail of how it is done in our paper, naturally. But the main thing to know about this method of management is that page tables in Linux are never freed. So any page table you allocate into your paging structure is going to be there forever. And that's the reason that's a good thing that our allocator makes sure that we are working in a relatively bounded area of the virtual address space. Okay, so IOVA Assignment doesn't scale. It's in a global lock, and we'll try and present three possible designs for allocating or assigning IOVAs. So our first takes ask the question of why do we actually need an allocator, right? Every buffer that you're going to map already has an address, its physical address. Why can't we map it in the virtual address that is equal to the physical address? We won't map physical pages that we don't want the device to access, but those that we do want, we can just map in the same place as their physical address. And to do that, we need to address two things. One is reference counting. Let's say you have a page and you've mapped this page twice in the IOMMU, and then you've went and unmapped it, one of these mappings. The device should still be able to access this page in the memory. And only once you do the second unmapping, you want to remove it and make sure the device has no longer has access. And to do that, you have to know how many mappings are alive in the system. And we do this reference count by storing it in spare bits and the page table entry. And we manage these bits and with the atomic operations, because we might have sharing on these last level entries. The second thing we need to get right is permissions. Let's say we have one page, we've mapped it once with read permissions, one with write permissions, and then we went on to unmap the write permission mapping. The device should no longer have the ability to write to this page, even though we don't want it to keep on reading from it. So we achieve that by noting that processors actually support larger virtual space than they do a physical space. And so we satisfy mappings for reading or for writing from different parts of the memory. So these two never collide. For our second IOVA assignment approach, we ask the question of what is actually allocating an IOVA. To allocate an IOVA for a range of pages, you just need to allocate the virtual page numbers for these pages. And that's essentially just allocating a unique range of integers that is as big as the range of pages you want to allocate. And to contrast it with regular memory allocators allocate a range of bytes in the memory, right? And these bytes have a unique integer range, the addresses of these bytes. No other allocation in the memory, no other buffer allocated would have the same addresses. And we can use these addresses as a unique range of integers and just completely disregard the backing memory. And so our second IOVA assignment design asks the question of why not actually use one of these general purpose allocators. They're out there, they're highly optimized, and we'll use the kernel-owned kmalloc, and we'll allocate as many bytes as we have pages. We'll use the address for our mapping and just disregard the memory itself. And hopefully that will simulate the general purpose highly optimized allocator. For our third design, we'll use the Linux allocator as a baseline, and we'll take a node from general allocators and just layer it with local caches, so we can reuse free the IOVAs without accessing a global lock. We just save them locally. And this has the upside of still packing allocations in the memory. Okay, so to evaluate, we are working on two more or less identical machines. Each has 16 Haswell cores and a 10 gigabit NIC. The server was where we'll change our designs, and the client will be a simple load generator. So for a running example, we can see that all of our designs actually scale quite well, linearly with a constant overhead. And when we look on Memcached workload, we see a very similar results. Our designs scale linearly right until the point where they hit the line rate. To estimate latency, we again turn to a TCP request response. But this time, we only run one instance per core. So each instance has its own dedicated core in both the server and the client. And each sends a byte, waits for a byte, and return. And on one core, all of our designs, as well as EOVAR, achieve the same latency as without an IOMMU. With 16 cores, EOVAR is actually have a higher latency, with 10 microseconds higher latency, while our designs all perform as well as no IOMMU. In terms of page tables, both EOVAR and magazines are by design packing page tables because they are based on the Linux allocator. And they allocate all the page tables in the first iteration. What we do here is run our 16-core parallel workload and measuring page table usage between iterations. The dynamic identity solution doesn't by design restrict page table usage, but because the driver allocates it maps buffers from caches to begin with, all of the buffers it maps comes from a cache, we keep on mapping the same buffers over and over again. When we introduce kmalloc to the same graph, we see that page table usage just explodes, and that's because we allocate bytes from a generic allocator from all across the memory. So because Linux doesn't free page tables, we actually do need a specialized allocator, even though this allocator, as we've seen in the magazine's case, can definitely take a page from generic allocators, the generic allocators book. To summary a design-specific exploration, we try to estimate subjectively how long it would take us to re-implement all of these approaches, and dynamic identity is the hardest one to implement probably because you do have contention on these slash-level page table entries and you need to manage them, the reference counts with atomic operations, and it's quite fine. Kmalloc, by contrast, is the simplest one to implement. To simply change IOVA alloc with kmalloc and IOVA free with k-free. And magazines is a relatively simple solution, and it has the obvious upside that it can control the page table waste. To conclude, while MMUs and IOMMUs are quite similar from an architectural point of view, they actually differ quite a bit because of the usage patterns, and we can't really use the implementations for MMUs exactly as they are for IOMMUs as well. And we have introduced the first IOMMUs management schemes that actually do scale, and we have tried to compare some of their properties. As future works, we list first getting strict invalidations done in a scalable manner, managing our page tables better, allowing us to free page tables back to the system while still doing it scalably. And if you think about it, all IOMMU-based approach for protecting your memory works on a page boundary. And you might want to be able to restrict the device from accessing arbitrary buffers in the systems that belong to someone else just because they happen to be collocated on the same page they have access to. And with that, I'll happily take any questions you might have.
Hi, Steve Muir, Comcast. This is interesting stuff. You made a brief mention in the middle of your talk that non-Linux OSes structurally have the same problem, but then you sort of didn't address those other OSes subsequently, in particular in your performance evaluation. Did you do evaluation of FreeBSD or OSX, even kind of like roughly to be able to say if Linux is especially bad or better than them?
Okay, so we've set off essentially from Linux, and we have evaluated indeed our work on Linux, but we wanted to see how it works on other operating systems. And Linux actually, with EOVAR in place, have the most distilled problem of all of them, because under the lock for IOVA allocation, with EOVAR you only do constant time overhead allocations within the lock, very minimal one. And with invalidations, you just skew your IOVA. So looking at the other OSes, we have only reviewed them statically, as you said. All of them do both these operations under a lock. So we assume that all of them will have the same problems. Most of these actually do whole lot more under the lock. None of them batch invalidations, for instance. All of them access the invalidation interface for each and every unmapping they do, or mapping unmapping they do. So yes, we have only reviewed them statically, but I cannot think of a case where they actually perform better having a lock on both of these.
So my follow-on question was going to be, so what you've done is actually obviously improves performance a lot and seems like a significant amount of implementation. And this may be totally out there and crazy, but it sounds like it would be kind of nice, based upon what you just said, if you could kind of take your new frameworks and actually plug them into, FreeBSD. Again, crazy thought, but it would be nice if there was reuse within the kernel of things like IOMMU stuff. I mean, is that even vaguely feasible?
So reuse between kernels? Like FreeBSD and Linux are distinct kernels with their own implementation.
I understand that they're distinct, but I mean, they're C code and they run on the same hardware, and so, I mean, it's not like it's totally
It's a good question.
insane,
It's a question for the FreeBSD community and the Linux community, right?
Well, it's a question, but I mean, for you as a sort of the designer of this, do you see that there's even common data structures, I mean, you're still talking about IOVAs and... Well, it just would be nice if you didn't have to someone else didn't have to reinvent all your work to make FreeBSD have these nice properties.
Well, I completely agree, and that's something the Intel guys that actually implemented support for this IOMMU should take into account. It is worth noting that different operating systems actually do have different considerations going into their management. FreeBSD, for instance, do free page tables, but they do it under a lock, and they would suffer significantly from that. Linux doesn't do that. It prefers to have better runtime, better throughput at the cost of having some leakage of page tables. FreeBSD, for instance, is also strict, and it will suffer from that in terms of performance, but it would get like a more perfect kind of security. So for Linux, I would feel more comfortable swapping this out one for one. For FreeBSD, it would take a more it would take one of the maintainers saying that he's fine with that, because we are actually changing security assumptions.
All right, thank you.
I actually had one quick question, and it's, I guess, related to something you say as future work, but I'm wondering if you have any ideas of how you might close that window where I've released an IOVA, but the TLB hasn't been flushed yet. I mean, do you have any ideas of how you might close that window, or?
Okay, so the problem here is the problem of if you once you remove a mapping from the table and you want to carry out invalidation, you only have a very narrow time to do that because it is part of your unmap workflow and want to return from unmap if you want strict semantic, you want it to be out of the IOTLB, and you don't really have a huge window to do it in. So in order to achieve that, I think what you would need to do is to change the semantic of your mapping interface. You need to allow some kind of a synchronization point in which the driver tells you in advance, I'm going to unmap that, but only now I'm going to assume it's out of the IOTLB and reuse the address. Some of this can be mitigated by taking page references to the page until it's invalidated, so it's not used somewhere else in the system, not reallocated as a whole. Some of it can be mitigated maybe for network flows with some kind of copying, but it would not be solved by the current interface for unmapping. That's my thoughts.
Great,
naturally.
thanks. All right, let's thank our speaker one more time. Oh, there's another question.
Just a sort of curiosity, because I'm not particularly familiar with this part of the kernel or how it's used. What's the sort of lifetime curve of these IOVA mappings? Like, are there some long-lived ones and some short-lived ones, or? Yes.
So the IOVAs that would go to the buffers and the rings are completely transient. They're there for for just one transaction, getting a packet, and then they're released. Some buffers are there for programming the network device, and then they will be long-lived. And you do have to synchronize it. You have synchronization points which you can carry out instead of unmapping. And some would be the rings distributors themselves, which are also longer lived. But there are buffers that gets mapped and unmapped for every operations which contains the data itself, unless you have very small packets.
Thank you.
All right, let's thank a speaker one more time.